Good day. I am Mr. Macjan Poblete and I am here to present my research about enterprise big data in partial fulfillment for the course MIT 620 Advanced Organization of Database submitted to Professor Rosicar Escober. And to begin, let's start discussing the background about big data. Big data is emerging from the realms of science projects at web companies to help companies like telecommunication giants understand exactly which customers are unhappy with service and what processes cause that dissatisfaction and predict which customers are going to change carriers. To obtain this information, billions of loosely structured bytes of data in different locations needs to be processed until the needle in the haystack is found. The analysis enables executive management to fix faulty processes or people and maybe be able to reach out to retain the at-risk customers. The real business impact is that big data technologies can do this in weeks or months, 4 or more times faster than traditional data warehousing approaches. The IT techniques and tools to execute big data processing are new, very important, and exciting. Now, let's move on with the discussion of enterprise big data. Big data is data that is too large to process using traditional methods. It originated with web search companies who had the problem of querying very large distributed aggregations of loosely structured data. Google developed MapReduce to support distributed computing on large datasets and computer clusters. Inspired by Google's MapReduce and Google File System or GFS papers. Hadoop is an Apache project written in Java and being built and used by a global community of contributors. Yahoo has been the largest contributor to the project and uses Hadoop extensively across its businesses on 38,000 nodes. Meanwhile, Dogcatting joined Cloudera, a commercial Hadoop company that develops, packages, supports and distributes Hadoop, making it accessible to enterprise IT. Now, let's move on with the definition of big data. Big data has the following characteristics. It is very large, distributed aggregations of loosely structured data, often incomplete and inaccessible. Petabytes, exabytes of data, millions or billions of people, billions or trillions of records, loosely structured and often distributed data, flat schemas with few complex interrelationships, often involving timestamp events, often made up of incomplete data, often including connections between data elements that must be probabilistically inferred, and applications that involve big data can be transactional such as Facebook or Photobox, and analytics such as ClickFacts or MERST applications. Now let's move on with the discussion of components of big data processing. Big data projects have a number of different layers of abstraction, from abstraction of the data through to running analytics against abstracted data. The figure shows the common components of analytical big data and their relationship to each other. The higher level components help make big data projects easier and more productive. Hadoop is often at the center of big data projects, but it is not a prerequisite. The components of analytical big data shown in the figure include packaging and support of Hadoop by organizations such as Cloudera to include MapReduce, essentially the compute layer of big data. Next, file systems such as the Hadoop Distributed File System or HDFS, which manages the retrieval and storing of data and metadata required for computation. Other file systems or databases such as HBase, a NoSQL tabular store, or Cassandra, a NoSQL eventually consistent key value store, can also be used. Another component is instead of writing in Java, higher level languages as Pig, a part of Hadoop, can be used, such simplifying the writing of computations. Next is the Hive, which is a data warehouse layer built on top of Hadoop, developed by Facebook programmers. Next is the Cascading, which is a thin Java library that sits on top of Hadoop that allows suites of MapReduce jobs to be run and managed as a unit. It is widely used to develop special tools. Another component is that it is semi-automated modeling such as CRX allows models to develop interactively at great speed and can help set up the database that will run the analytics. Specialized scale analytic databases such as Greenplum or Netezza with very fast load and reload the data for the analytic model is another component. Lastly, is the ISB big data and analytical packages such as ClickFacts and MERST run against the database to help address the business issues like the customer satisfaction issues mentioned in the introduction. Transactional big data projects cannot use a Hadoop as it is not real-time. For transactional systems that do not need a database with ACID guarantees, no SQL databases can be used. Though there are constraints such as weak consistency guarantees or restricting transaction to a single data item. For big data transactional SQL databases that need the ACID guarantees, the choices are limited. Traditional scale-up databases are usually too costly for very large-scale deployment and don't scale out very well. Most social databases have had to handcraft solutions. Recently, a new breed of scale-out SQL database have emerged with architectures that move the processing next to the data, in the same way as Hadoop, such as Clastrix. These allow greater scale-outability. This area is extremely fast-growing, with many new entrants into the market expected over the next few years. And we're done with the components of big data processing. Now let's move on with the big data analytics complements data warehouse. This figure shows the big differences between the traditional data warehouse and big data analytics. First, with traditional data warehouse, the sources are mainly internal, well-known and structured. Data fields have known and often complex interrelationships and the data is stable. Most of the data is historical with 10% or so reflecting new transactions that are being added to the data warehouse. Many reports are done on production basis. The main elapsed time is devoted to the production runs to produce the data marts and reports. Next, with big data analytics, the problems are very different. First, the data can be anywhere and is of unknown quality and or utility. The initial iterative stages will be to find out about the data and create and improve a data model. In the introductory example, the user may be investigating the causes of customer churn. One hypothesis could be that poor call center experience is a major contributor. Every interaction a customer has been making with the organization is traced to find common factors between the customers that stay and the customers that leave. The working principle behind Hadoop and all big data is to move the query to the data to be processed, not the data to the query processor. Every step of the process means the database is changing and needs to be reloaded. The analytic models are larger and require very large amounts of memory to operate. The database requirements are very different. There is a big emphasis on databases such as Greenplum, which feature very fast data loading. The data is laid out differently across the nodes of a scale-out topology to reduce the data movement and locking, and queries are moved to the nodes, giving the database engine much higher scalability on commodity hardware. Lastly, I will be discussing about the positioning of database. The figure gives a positioning of database that support transactional and analytical workloads and show that support of loosely structured and scale-out architectures are essential for big data initiatives. Traditional data warehouse and big data analytics are complementary to each other and feed each other. Traditional data warehouses are a source of data for big data projects. If new data, which is valuable on an ongoing basis during a big data project, it should be brought into the traditional data warehouse, cleaned up, and take advantage of the production capabilities of traditional database. This concludes my report. Thank you for listening and goodbye. Have a good day.